What's up everyone? I am back with another repair video. Hope everyone is doing well. So I've actually done a video not all that long ago on this type of equipment, different make and model, but as you can see this is a thermal cycler. Now I went into what thermal cyclers are in that video, so I'm going to try to keep it brief, but basically thermal cyclers, also referred to as PCR machines. So PCR stands for polymerase chain reaction. These machines are used for amplifying strands of DNA, making copies of DNA. And again, I won't go into too much detail on how they work, but basically what they do is they will, there is a reaction module that sits in the instrument. Actually, this one is missing it, but it's a reaction module that is temperature controlled via Peltier elements usually, and they will ramp up the temperature of that reaction, that polymerase chain reaction. They'll ramp it up, they'll bring it down, and they'll just cycle that over and over again, hence the name thermal cycler, to create these copies of strands of DNA. That's what this machine does, and this is a Bio-Rad C1000. Now, we don't have any of these in our lab. I actually bought this on eBay for $35. I knew it wasn't working, so I thought it would be fun to repair it. I was also working on a newer generation of this instrument. So the current generation that's out now is called the C1000 Touch. And it's pretty much the same, except it has a touch screen. So it's a little bit newer, more modern, but they basically do the same thing. They look the same as far as their size. And what's different about these compared to the other instrument that I worked on in that last video is the reaction module can be removed. Alright, so that kind of allows you to customize the instrument a little bit. So for example, with PCR plates, you can get them as a 96 well plate or a 384 well plate. And so what this instrument does is, if you can buy different reaction modules. They aren't cheap, by the way, and you can get one that's for 96 well, one that's for 384 well, one that's for deep well. So it does allow a little bit of customization. So that's the main difference between this guy and the other one that I worked on, besides the fact that they're from different manufacturers as well. Now, this guy, the only thing I know about it is that it doesn't power on. I think the fuses are blown as well, the main fuses, but that's about it. Don't know much about its history. Clearly, wherever it was stored wasn't in the cleanest area, so there's that. But yeah, so it doesn't power on. So we're going to investigate that. We're going to take it apart, take a look at the circuitry. I'll kind of go over how these things work on that level, and then we'll get into some troubleshooting. Alright, so let's get started. Alright, so we finally got the main board out, and figured we'd kind of go over, do a brief visual inspection, see what we can make of the topology, and then we can, after that, go into the actual testing and fault finding. But yeah, let's get started with this. So I have worked on a similar unit to this C1000. It's the CT1000 or the C1000 Touch. It's the newest model, and so there looks like some similarities right off the bat, but definitely some differences. For one, on the newer version, the power supply is separate from the main board. So this one, it's integrated into the board, so that's already very different. But I'll kind of go over what some of the other differences as we move along. But yeah, let's just get started here with the inputs. AC input, mains input. So that's where this connector goes, and that goes off to a EMI filtering module, and you know, it looks like we've got some what could be X-class capacitors, maybe some of these little guys down there, or also that. You've got your bridge rectifier right here. Number of transformers, this big one here, probably the main transformer, this secondary transformer, likely for the auxiliary winding or power to get this thing started up. You got a current transformer here too. Oh, forgot the fuses. You've got two fuses, one for live and neutral. Not sure what that little fuse is for. You got another little fuse here. Let's see what else. We've got some big MOSFETs here, likely the primary switching MOSFETs. Some big filter caps, the main filter caps here. And then we've got over here some more TO247 type semiconductors. This is a MOSFET. This is likely the boost converter for the PFC. So normally you'll see that one MOSFET and then one diode, fast switching diode, like a Scotch key diode. Now you've got some power management ICs or PWMs. Got some more of these here. Yeah, they could be gate drivers because you got two here for these matching the MOSFETs. This is a 2844, UC2844, so we got another current mode PWM. Yeah, so this is all the power supply. This whole area right here. Okay? Pretty cool. And so then, as we look at the rest of the board, this is more so, of course, for the actual controlling of the functionality. The rails on this board, you've got a 40 volt rail, and then 15 volts, and then minus 15. So I believe here you've got a 15 volt regulator, and then another negative 15 volt regulator. Getting on to more of the digital side, you've got a microcontroller. This is a HC12 series micro, same as the newer board. You've got a complex programmable logic device, probably for the glue logic. This is a USB interface, RTC battery there, and then you've got these two what could be microcontrollers of some kind. Again, they could be more for the thermal control, driving the TEs. And of course you've got the output, so you've got three Peltier elements coming out here, three here. You've got the chokes for those, there and there. Alright. And yeah, I mean, we can flip this guy over. Got some flux residue up there. But and not sure what these are. These look expensive though. And then this looks like SRAM. So probably some more logic devices down here. But yeah, that is it pretty much. And kind of summing that up, simplifying things a bit. But it's time to get into this and figure out what's going on. Let's start checking for shorts. Now, again, as I mentioned earlier, we know that both the two input fuses, they're 10 amp fuses, were blown. So let's check for shorts across live and neutral. Checking live and neutral right now. No short there. Let's check the lower voltage rails. So let's check the 40 volt rail for short. Okay, so it's not shorted. We're charging up a capacitor there. Let's check the 5 volt rail. It's not short. 15, not short. Negative 15, also not short. All right. Let's see. Let's just check this fuse here. Okay, that's good. And check this fuse. That fuse is good. All right. Let's check the bridge rectifier. This should be okay. Oh. Uh-oh. So it is short on the DC side. This is the buck converter diode, I believe. Yep. So that's good. Oh, and so this is the buck converter MOSFET. This could be the culprit. That's what I'd like to start with first. I'm going to remove this heatsink, and I'm going to remove this this MOSFET from the buck converter. I'm sorry, boost converter, and test that out of circuit. Well, guys, I think we found our culprit, or one of the culprits. So this is, I removed that MOSFET, and we no longer have a short. Yep. You can check the MOSFET itself, of course. That would be a good idea, right? So that's it right there. And again, I apologize for the horrible camera angle. But yeah, this guy is very short. All right. Okay. All right. So the closest thing I have in stock to this guy is this guy right here. Alright, y'all, so I am also lacking in the fuse department as well. I did not have two 10 amp fuses, especially those smaller ones. But I got a 6 amp, two 6 amp fuses in there, and we're not powering it up yet with any of the fans or the Peltier elements, which is really what's going to take the bulk of that power. So it should be fine just for testing the voltage rails. Alright, so we got our multimeter hooked up to the 40 volt rail. Let's see what happens. I'm going to power this thing on. The wide angle shot. Let's see if anything explodes. And there you go. Nice. So that MOSFET is holding its own, it looks like. The 40 volt LED is active. Oh. Oh no. Oh no. Something just died. Oh man, something just died. Yep. Alright, y'all, so it looks like, I know, I'm sorry guys with the camera angles, but it looks like this MOSFET has shorted, the one we just put in. Yep. So that MOSFET took out one of the fuses. I've been saying this for a long time. I need a in-circuit lamp or in-series lamp tester to save me some fuses. Alright, again, you'll have to excuse the camera angle here. This rig that I've got is practically falling apart. This guy right down here is a UCC 3817. That's a PFC controller. And I traced the circuitry. The driver for that guy goes to, I don't know if you can see that, but there's a nice DIP 8 that's a gate driver, which is driving that MOSFET, all right, which is shorted. So we got to figure out what is causing this MOSFET to short out. And it doesn't happen immediately. It's almost like it's being driven to failure, so it could be, is it the PFC controller gone bad and it's just, or is it something else? So that's what we need to figure out. Alright, y'all, so I popped in another MOSFET to replace the one that is shorted. This guy right here. And I did a bit of probing around the circuit. I did power it on without the MOSFET installed, just making sure that the PFC controller is getting the correct voltage, the reference voltage it's outputting is correct, the oscillator frequency seems okay, so everything's, for the most part, looks okay. So a couple things I did find out though is how the startup works, or the power on power off switch. So when you have this thing plugged in with the switch off, there's still power getting, the voltage is still being applied to the board. It's just that the PFC circuit is off, which is a bit misleading because there's this LED in the back that says 385 volts active that is lit even when the power switch, this guy, is off. But it's not actually 385 volts, it's just 160 volts because it's just at the mains voltage. Interesting thing about this switch, so you would think that when you're doing powering with a main switch like this, usually you think in the on position that the switch is closed. Well, actually with this switch it's open. And so I was kind of tracing out the circuit a bit just because I was curious, and this is what I came up with a bit, and you can see this is really the area of interest. This is the switch, the mains switch, quote unquote mains. It's not at mains voltage, but you've got the main filter cap, or one of them. There's 3 in parallel, these large caps here. You've got these 2 pull down resistors, and then you have the OVP, over voltage protection, enable pin. So if this pin falls below 1.9 volts, it basically disables the drive, or the output to the boost converter MOSFET. So if you close this switch in the off position, you're bringing this to ground, so that's going to pull this down well below 1.9 volts. With it open, which is the on position, it sits at 7.5 volts. So thought that was interesting. I could show that now, actually. So now it's off. All right. And I'm gonna probe the enable pin. I'm just gonna call it the enable pin. You can see it's at 0.5 volts, almost like a diode drop, and it might be because that diode sits between the OVP and the ground. So that could be why that is. If we power it on, we open that switch. It sits at 7.6 volts. All right. So now that I'm going to turn it off before this thing kills itself. But I think now would be a good time to watch this PFC controller while we power it on via the scope to kind of get a better idea of what's going on. Is it going to short itself out again? Let's hook up the scope, point the camera at the scope, and we'll see what's going on. Okay, so we got this is the setup currently. Got our probe on the gate to the PFC MOSFET. Also, I've added in the power analyzer just so we can monitor the amount of current that this guy is pulling. Currently it is on. Well, there is mains voltage applied, and it is only outputting 5 watts, which seems normal for standby. And so that's also why we don't see any there's no nothing is driving this MOSFET. This is at the gate, no signal. So let's power this guy on. Oh, wrong. This is my horrible camera rig, by the way, so this is why we are using such. This shouldn't just come right off. It's broke, so if yeah. Anyway, but yeah, let's power this guy on. All right. So that seems like a fairly high. It's up to 40 watts. Oh, look at that. That is interesting, and we're getting a very odd signal from or sound, I mean, from the board. Can you hear that? Very strange. Oh, ho. Okay. Oh, okay. Holy shit. Wow. Wow. What just happened there? Oh my god. Wow. Oh man. Magic smoke released. Where did that come from? I guess. Oh, okay. I see. This fuse just went up. Oh my god. Okay. All right. All right. Well, after that incredible fireworks show, what started smoking even a little bit of a flame was a fuse. Starting to have a nice collection of blown fuses here. It's this 500 milliamp fuse. I was suspecting the circuitry that is part of that puts the unit into standby mode. So when it's in standby, you do need the other power management ICs to be on. So you need that lower DC voltage somehow. And that is done with another PWM. Let's just flip the board over real quick. See if I can. Oh, there he is. So this U2844 right there. And the VCC for that guy is separate from the other VCCs. That one gets its voltage from the rectified DC from the main bridge rectifier. So you're in standby mode at roughly 160 volts DC. And then it is stepped down through a series of resistors, these big guys, and then when these are these resistors, that LED that says active 385 is in the path to this, and then it goes to the VCC of that PWM, which is on the you guys can't see what I'm pointing at. It's right here. That's the bottom of it. So I kind of suspected that it had something to do with that circuitry. Wasn't sure what. So I just kind of started probing around, and I think I found a potential culprit. This guy right here is a P-channel MOSFET, ZVP 2106. And check this out. So it is shorted from drain to source, which is a problem. Why that component failed is another matter. I'm not sure. A secondary fault. It seems like it's time to order some parts. I need to order a bunch of fuses. I'd like to order this PFC controller. Definitely this N-channel MOSFET. Maybe a few others that I don't have in my parts bin just to have on hand. But, yeah, that's kind of where we're at with this guy. Because I'll check, but I definitely don't think I have anything like that. Alright, so I removed that MOSFET. Let's power it on. Oh. Well, that's interesting. Alright, so I figured we could take a quick look at the current mode PWM, this UC 2844. Now this is the PWM that is going to be providing that initial voltage, low voltage, for power management ICs so that this thing can power on. Power on the rest of the board, I mean. So, let's just start with, the timing capacitor, the CTRT output, and there it is. That looks good. This is the, let's see, output. Yeah, that looks pretty. Yep, very nice. So, and then of course you've got VCC, which at 17.4 volts. So yeah, I mean, that all looks great. So, interestingly, there is no, for example, if we look at the PFC controller, there is no VCC voltage, no supply voltage to that controller. And that goes for any of those, the other PWM that I believe is driving the primary switching MOSFETs. Yeah, there's no voltage. What's the deal? So after looking at this again, it's a bit more clear what this MOSFET was doing. It is providing this is it where it was. This is the source pin and drain here. If you follow this all the way up, well, there you go. Actually, this is what I just missed. This pin right here, that's VCC, and so it goes to this little resistor here. I think that's a 200 ohm resistor. Yeah, So with this guy removed, it is not able to supply power to that rail. We need that MOSFET. It's definitely the culprit. Secondary fault for sure. And the primary fault, we have some ideas, but we're still not 100% sure. Alright, so we'll have to stop here for a bit and we'll pick back up when we get some parts in. One more thing while we're waiting for the parts. So figured I would talk about this relay a bit. Let's just go over that real quick. You see relays like this a lot in the on the primary side of the supply, and they mainly serve one purpose, and that is, so in this case, for example, you've got this big power resistor here, right? It's a 47 ohm resistor, and its purpose is to act as a current limiter. You normally, when you power something on, or this can happen when you power something on, you get a inrush current, and that is what that is limiting to mitigate any unwanted effects of that current. But once this device comes on and the current starts to stabilize, that resistor is really no longer needed. So the relay is actually, when this closes, both the contacts of the relay are the resistors across them. And so you have 47 ohms across these contacts. When this relay closes, it becomes a short, which effectively takes the resistor out of the equation. And so, you know, because if this resistor was still left in circuit, you didn't have this relay here, it would generate a lot of heat, or potentially couldn't handle the load generated by this board, because you've got the block, which is generating a lot of power along with the fans. So, you know, it's an efficiency thing as well. And the way that this relay gets turned on is, once the PWM is started up, you can actually see down here you've got that test point number 3. Well, that's the 18 volts that should have been delivered to these other power management ICs that is no longer being delivered due to that missing MOSFET. But anyway, you can also see that 750 ohm resistor R201 that takes that roughly 18 volts, steps it down to about 12 volts, which is what this relay requires to switch on. You can actually see the lead, the trace going to the coil that turns switches the relay on. Not something too complex. It doesn't need to be all that complex. It's just, as soon as power is delivered by the PWM, this relay should come on. Figured I'd go over that because you do see these a lot in power supplies. Well, I'm already back. So, parts did not come in, but I actually had an idea to continue our troubleshooting while we wait for some parts to come in. And what we need is power to our power management ICs. It's not being delivered because of that MOSFET that failed. But what if we injected power to the VCC, that rail, with an external power supply? And so that's what I'm gonna do. Give this a try. There is a connector right there called J4. The middle connector is power ground, and then pin 1, I guess, is basically on the VCC rail. I think we'll start with powering on the mains voltage, and then bring this guy online and see what happens. If this works, it's actually pretty good for troubleshooting because we have direct control of limiting the current. So if the reason for that MOSFET shorting was due to over current, we can limit that there to prevent any further damage. So that actually makes for a good troubleshooting tool. But let's just see if it works. So let's find that switch and give this a try. Alright, I found the switch. Now again, we're going to start, it's off. So we're going to start with just powering this guy on. So let's give that a try. We still have our power analyzer attached. Okay, so far so good. Now, let's give this a try. Let's power on our DC supply and see what happens. Oh! And that fuse blew. Wow. Perhaps we limited the current not quite enough. Alright. Let's try something else first. We're going to start by limiting the current very low. Okay. It's 100 milliamps. And we're going to see what happens. Alright. So, yeah, so clearly something isn't right. It can't. Oh, and I'm smelling something burning. This is where having a thermal camera would come in really handy. I can smell something. I don't know what is causing that. Ooh, yep. Oh man. Ooh, yep. There it is. It's that. It's the gate driver. Jeez, that's getting really hot. Gate driver to the PFC MOSFET. It's getting super hot. Alright, so we removed that gate driver. I suspect that once we power this guy on, it should do fine. Of course, now it's not going to drive this MOSFET, so we're not going to see the the rest of the board come up, but we shouldn't see any more blown fuses or any smelly magic smoke. So let's give this a try. Alright, I've got everything connected, so let's just power on the VCC first and see what happens. And perfect. It's able to do 17 volts just fine. That looks great. Alright, so let's power on the rest of the unit. And we shouldn't see any blown fuses. Okay. And so far so good. We should be able to at least see the output to the gate, and it's not going to make it to the MOSFET because again we removed the gate driver, but let's check that as well. So I'm going to prop up the camera at the scope so you guys can see that. Alright, so right now I haven't turned the switch on yet, but we're just going to check a couple things on the PFC controller. So that's VCC, what we already know. There's our nice oscillator signal. Looks good. We're going to power this guy on. We should see a signal here. And we don't. Alright, so I think I found the culprit. Unfortunately, when I removed that gate driver, it was a bit of a fight. Underneath it, there is some pretty big traces for the either the ground. I think it's either ground or the VCC. I forget. But anyway, it did pull up a couple traces on the top side, and we'll fix those. But what happened is it removed the trace or link between that diode there and that tantalum cap, and so I just added a jumper there, and the driver, when this power switch is on, it started outputting a signal. It does appear that the chip is working properly, and I'll just show you guys that now. Okay guys, so I had another great idea. Technically, you don't need a gate driver to drive this MOSFET. I mean, even in the datasheet for the UCC 3817, it's just a 20 ohm resistor directly to the gate of the MOSFET, the switching MOSFET. So it's not necessary. But anyway, I decided to basically short the input and the output to those, to where that gate driver was. I did use a current limiter to short them. We'll see what happens. Alright, let's give this a try. Alright, what do you guys say we give this a try? This could either be really bad or really good. So, we got our external power supply on. Next, just want to make sure this switch is off. Main switch is off. Let's turn on the isolation transformer. Okay, so far so good. Let's put our safety glasses on. See what happens when I turn this guy on. Wow. It's working. That duty cycle looks a little high. I mean, we're pulling 30 watts, which isn't an enormous amount. Got 45 volts. These MOSFETs should be on a heatsink, so I don't want to keep this going too long. I think we might be good. Alright, I might be getting a bit greedy here, but I kind of want to see if we can power on the display. So I've got a fan going to help remove some heat. I'm just too lazy to put in the heat sinks at this point. Besides, to do them right, I'm gonna have to replace the compound on here. And yeah, so anyway, let's see if we can get this to work. It shouldn't require that much power. Again, it's not like we're trying to turn on the block or anything like that, but who knows. So it's only right now, it's only asking for an additional, the power consumption hasn't changed much. Maybe 5 watts more. It's booting up. Wow. Oh man. Of course it's going to find errors, but it recognized the serial number. Firmware is intact. Great sign. So it looks like if we can get this power supply sorted out, we should be in good shape. Things are looking up. Alright, so we got our gate driver in, replacement gate driver right there, and a new PFC controller. That one we did not tear up any traces for, or looks no copper was damaged on that replacement, so we made up for that one. And yeah, I had to pull some funky stuff here since I ripped up some traces. I know it's a little funky, little sketchy. PNP transistor, there it is. So we are good to go. Also got in the correct size fuses, two 10 amp fuses, and yeah, let's power this thing on and see what happens. Alright y'all, so got everything hooked up. We got our scope on the gate of the PFC MOSFET. We've got our meter on the 40 volt rail. We've got the power meter on the mains, and we are plugged into our isolation transformer. So why don't we power this guy on? Watch out for fireworks. Okay. So far so good. On standby we're at roughly 5 watts, which is normal. Okay. Let's see. The PFC circuit will turn on when we turn on the power switch. There it is. Roughly 35 watts, which I believe is normal. Here is our gate on the PFC MOSFET. Look at that duty cycle. That duty cycle just kind of freaks me out a bit. It just seems like it's too high. 40 volt rail is out steady. So why don't we do this? Why don't we get the heat sinks installed and power on the front end display board? Let's do that. Alright, we're all back together on the main board. Self-test in progress, and we're booting up. We're still monitoring the PFC MOSFET, and we are live. There it is. It's recognizing that its serial number, it's obvious. Now, unfortunately, without the block, we really can't test this guy to its fullest. You know, we really can't put it through any serious load test. The block is what is taking, the thermal block is what's really using up the brunt of the power. So I can't say with 100% certainty that this board is okay, but things are looking good. This guy's getting pretty warm. This is the heatsink for the primary switching MOSFETs. This is the gate to the one of the primary switching MOSFETs. Looks pretty good. We're still maintaining a very stable 45 volts on the 40 volt rail. Same with the power consumption. Well, we are in service mode now, which, by the way, the password for service mode on the C1000 units is just Bio-Rad in capital letters. For the CT1000 units with the touchscreen, it's Bio 94547. So the password is on these Bio-Rad instruments varies. Sometimes it's just 94547 Bio-Rad, and then variations of that. So you just got to kind of play around with it, but that's what it is for this one. And so yeah, you've got, you know, your 40 volt sense. This says it's 44.33. I trust my meter. VCC 5 volts, looking good. The 15 volt sense is 14. Even the temperatures, well, the heat sinks, amp 1 and amp 2, so that's just these long heat sinks. I mean, they shouldn't be getting hot. And then the power supply heat sink is that one right there. That one is sitting at 32.6. So interestingly, it somehow knows it's reading these temperatures. I don't know how, these phantom temperatures, because there's no block at all. You can clearly see there's no power being delivered, so That's odd. But everything checks out. Alright, so I connected the fans and ran. What's cool about this unit is during the diagnostic test you can sort of pick which test to do within that test, whereas on the newer models it's just one test. It does a few different functions. So because really the only thing I could check was the fans, it'll run them through low, medium, and high. Right now it's on high. Interestingly though, we only got one fan running. I'm going to try and swap connections and see if this is fan specific or something else is going on here. Yeah, so no, it's definitely not the fan at fault here. This is the other one. I just swapped the connections, so there's something odd going on here. Alright, so I just wanted to do a quick check of some things to see if we could verify. Sorry about that. If we could verify if it is a connection issue, and I don't think it is. So this is the 17-volt supply for the fans. That looks good. But as we move down here to this bank of capacitors, this is the one going to the fan that's currently running. And we only have, so we had 9 volts there, right? And then only 0.6 volts there. What if we increase it? So we're at 9.95. But this one stays the same. Yeah, now we're at 12.94. But nothing there. So I think before I reassemble this, let's maybe take a look we'd have to map out this circuit a bit to see what's going on here. Alright, you guys, really thought we were in the clear when I finished up with those replacing those components, but clearly we're not. And so I went into look into this a little bit further. You've got these two low voltage dropout regulators right here and here. These are LT 1963As. Yeah, low noise, fast transient response LDO regulators. They have an enable pin, pin 1, and if that is low, I believe it shuts it down. So both of these were low before I started the diagnostic test again. Alright, so that's the bottom one. And there is the other one. So the bottom is U255, this is U256. So the bottom one, 17 volts going in, 0.58 volts going out. We saw that. This one, 17.67 volts going in. You got your 9 volts going out. So I don't think this is a problem with the regulator. It's whatever that enable signal is, where that's coming from, that's the culprit. Alright, y'all, we're gonna test the LDO. So what I'm gonna do is I've got 5 volts at the end of this probe for my DC power supply. I'm going to connect it to the enable pin of this LDO. We've also got a meter here that is measuring the voltage across that's being applied to the fan, the non-working fan right now. So watch this. I don't know if you can hear it, but the fan that was off just came on. However, it's 3 volts lower than the other fan. The other fan at low speed is at roughly 9 volts. Medium speed, it's at 10 volts roughly, and then high speed, it's at 13. So we're still missing something. Now, I did check the other pin, which let me see what that other pin, the last pin. Last pin is sense / adjust. And I thought that could potentially be the case, but I checked the working fan's LDO as I went from medium, low, high to check the voltage adjust, or the adjust or sense pin. And it stays at 1.2 volts roughly throughout the end. Doesn't matter what setting it is. Now, I'm using my meter right now to check the, well, let's do this actually. I can show you guys. Let's just disconnect briefly the voltage across the fan. So this is the working LDO. You can see 1.2 volts. Now let's turn on our other fan. You can see we're at 1.2 volts. No difference. Alright, so I was doing a bit more probing around of the circuitry involved in controlling these fans. And so the enable pins for both of those low voltage dropout regulators, those LT 1963As on the other side of the board, they do connect directly to the microcontroller. And that's the microcontroller right there. It's an MC9S12A or HC12 series. But yeah, so for the working one, I believe it's pin 1. The enable pin is pin 1. For the one that's having trouble right now, it's pin 3. So, you know, there's nothing else in between there that could be causing the issue. It's the signal's not coming from the microcontroller. That's it. But that's not the only signal coming from the microcontroller to control these fans. So I did a little bit more tracing out this circuit, and you've got this array of logic level MOSFETs. These are NDS 355ANs. And so you've got these two, Q220 and Q219. They're associated with the working fan. And then you have Q217 and Q218 that are associated with the non-working fan. The gates of these MOSFETs, these are the gates right there. And then they go to this gate resistor, which then goes on to the microcontroller. Same for Q219 connects to this gate resistor, and then that goes on to the microcontroller, and so on and so forth, alright? So all those go to the microcontroller, and these transistors are turned on, and one will be on and one will be off for a low setting, then the other one will be on, the other will be off for a medium setting, and then they'll both be on for a high setting. And I'm going to show you guys that right now. So let's do that real quick. Alright, so I just turned on the fan, the diagnostic test. It's on the low setting now. Now I'm going to enable the other fan, so you can kind of hear that just came on. And then we're going to probe these transistors, the gates of these transistors, or the gate resistors. Alright. Alright. So, sorry about that. So that is one Q220. Nothing going on there. Q219. So that guy is on. Alright. Now if we go to the other ones, we got nothing. And we got nothing. So there are other signals not coming from the microcontroller as well. Now I've just increased the speed, so we're gonna do this again. Okay, so this guy is on, and now this guy is off. So they've switched. And then of course, but nobody's home on these other two. Alright, this is why the fan speed for that non-working one, even though we enabled it, the speed isn't increasing. Now if we go to high, you can see that one's on. And the other one's on. Alright? Not going to do it again for the other one because you get the idea, but yeah, so that's what's going on here. Those transistors over there are involved in adjusting the fan speed. And so now we've got 3 signals coming from that aren't being delivered from the microcontroller to control these fans, which is interesting. Now I've actually showed that this circuitry is working. Had signals been delivered via the microcontroller. I can actually show you guys that now. So what I'm going to do is I've got a 5 volts at the end of this probe, limiting the current just to not short anything out in case this microcontroller is good. And we're just going to apply it to those gate resistors to match the speed of those other fans, the other fan. Alright, so I've got the diagnostic test going again. Now it's running on low, and I'm probing the positive lead of the non-working fan. You can see it's at 6 volts, which it should be at on the low speed. It's 9, should be at 9 volts. Now, if I take this test lead with 5 volts at the end and put it to that one gate resistor, one of the gate resistors, you can see now it goes up to 9 volts. Now, let's just go to the medium. If I put this guy on the other gate resistor, you can see it steps up to 9.8 volts. And I don't have another test lead. I don't have 3 hands. Otherwise, we could do up the highest setting, which is 12 volts. But you get the idea. Alright, so at this point in the game, you know, there could be something wrong with the microcontroller. Are all those outputs damaged? It seems a little unlikely, but who knows, especially when you consider that all the circuitry appears okay. The microcontroller is definitely working in some capacity. But without the reaction module, can't really do much additional testing. I would really need that to kind of get a better idea of the state of the microcontroller. You know, excuse me, the unit is recognized by the front end controller. You know, it recognizes the serial number. All of that information is stored on the main board. But you know, the microcontroller, this one at least, is really just there for controlling the you know, all of the thermal control for the block and the fans. Yeah, there could be a lot more wrong with it, is what I'm getting at. But again, without that block, it's going to be really difficult to troubleshoot it any further. So I think, unfortunately, this is where this repair is going to have to end. I enjoyed working on it. This was more of just a fun project for me because we don't even have any of these units in the lab. So this isn't and that's another reason why I'm just gonna stop it here. So it's not like this is actual work, but you know, it is applicable for sure. So yeah, but we did fix. It looks like we did fix the power supply, which is great. And if I do get my hands on one of those reaction modules, I'll definitely do another video on troubleshooting this guy a bit further. But again, without that, it's really hard to really test that micro to see what's going on. So yeah, I hope you guys found this interesting and maybe learned something about these instruments. You guys have any feedback, please, as always, leave it in the comments. And thank you guys for watching, and I'll catch you at the next repair.